Welcome, fellow ocean explorers, to today's journey into one of Earth's final frontiers. Whether you're navigating the highways as a truck driver, unwinding after a challenging day at the office, or simply seeking solace in the mysteries of our planet, you've found the right place tonight. Take a moment to let us know where you're listening from. Drop your time zone and country in the comments below. If this content helps ease your mind and guides you toward peaceful rest, a gentle like or subscribe would mean the world to us. Tonight's visuals will complement our exploration, but close your eyes if you wish. The stories themselves will paint vivid pictures in your imagination. Tonight, we descend into the abyss, into waters so deep that sunlight has never touched their secrets. We're embarking on a voyage to understand why over 80% of our oceans remain as mysterious to us as the surface of Mars. The deep sea isn't just unexplored, it's practically alien, harboring creatures and phenomena that challenge everything we thought we knew about life on Earth. Picture this. You're standing at the edge of the ocean on a calm evening. The water stretches endlessly to the horizon, reflecting the last rays of sunlight. What you're seeing represents less than 5% of the marine environment. Beneath those gentle waves lies a world so vast and mysterious that we've mapped more of the moon's surface than our own ocean floors. The deepest parts of our seas could swallow Mount Everest entirely, with room to spare for several more mountain ranges stacked on top. The ocean's average depth reaches about 3,688 meters, roughly 12,100 feet, but in places like the Mariana Trench, the seafloor plunges to crushing depths of over 11,000 meters. That's more than 36,000 feet down, where the pressure becomes so intense it could flatten a human body in milliseconds. Yet even in these seemingly impossible conditions, life finds a way to not just survive, but thrive in ways that boggle the scientific mind. Why haven't we explored these depths? The answer lies in a combination of technological challenges, extreme costs, and conditions that make outer space seem hospitable by comparison. When we send humans to the International Space Station, they experience zero pressure. Deep sea explorers face the opposite extreme, pressure that increases by approximately 1 atmosphere every 10 meters of descent. At the bottom of the Mariana Trench, the pressure reaches over 1,000 times greater than what we experience at sea level. This crushing environment has demanded the development of specialized vessels that cost millions of dollars to build and operate. The famous bathyscaphe Truist, which first reached the deepest known point on Earth in 1960, had walls nearly 5 inches thick just to prevent implosion. Even today's most advanced deep-sea submersibles can only carry a handful of people and stay submerged for limited periods. But pressure isn't the only enemy of deep-sea exploration. The absolute darkness down there is unlike anything most of us can truly comprehend. Sunlight completely disappears at around 1,000 meters depth, creating a realm of eternal night. The temperature in these depths hovers just above freezing, typically between 1 and 4 degrees Celsius. Imagine trying to navigate and conduct scientific research in a pitch-black, freezing environment where a single equipment failure could mean death. The logistics alone are staggering. A single deep-sea expedition requires massive support vessels, specialized equipment that might cost more than luxury homes, and teams of highly trained specialists. Weather conditions on the surface can scrub missions entirely, since even the most advanced submersibles need calm seas for safe deployment and recovery. Ocean currents at various depths can push vessels off course, making precise navigation incredibly challenging. Yet despite these obstacles, the glimpses we've caught of the deep sea have revealed wonders that seem pulled from science fiction. Bioluminescent creatures create their own light shows in the darkness, painting the abyss with blues, greens, and ethereal whites. Giant tube worms, some reaching lengths of 8 feet, cluster around hydrothermal vents, where water temperatures can exceed 400 degrees Celsius. These vents spew chemicals that would be toxic to most surface life, yet they support entire ecosystems that exist completely independent of sunlight. Speaking of hydrothermal vents, their discovery revolutionized our understanding of life itself. Before 1977, scientists believed all life on Earth ultimately depended on photosynthesis, the process by which plants convert sunlight into energy. Then researchers stumbled upon these underwater geysers and found thriving communities of organisms that derive energy from chemicals, a process called chemosynthesis. These vent ecosystems suggested that life might exist in environments we previously thought uninhabitable, influencing our search for extraterrestrial life on planets and moons throughout our solar system. The creatures living around these vents defy conventional biology. Pompeii worms build their homes in temperatures that would cook most organisms. They've developed unique relationships with bacteria that coat their backs, providing both insulation and nutrition. Some deep-sea fish have evolved transparent heads, allowing them to see upward through their own skulls to spot prey silhouetted against the faintest glimmers of light from above. Then there are the giants of the deep. The colossal squid, larger than its famous cousin, the giant squid, roams the Southern Ocean's depths with eyes the size of dinner plates. These eyes, the largest in the animal kingdom, are perfectly adapted to detect the faintest bioluminescent signals in the abyss. Their tentacles sport rotating hooks that can tear flesh from prey or predator alike. We found evidence of epic battles between these massive cephalopods and sperm whales, but we've never witnessed such an encounter in the wild. The Japanese spider crab scuttles across the deep Pacific floor on legs that can span 12 feet from tip to tip. These arthropod giants can live for over a century, slowly growing in the cold, stable environment of the deep sea. Their longevity hints at how different time moves in these depths, where seasons are meaningless and change occurs at geological pace. But perhaps the most mysterious creatures are those we've barely begun to understand. Vampire squid, despite their ominous name, feed on marine snow, the constant drift of organic debris that falls from the upper ocean layers. Their name comes from their ability to turn themselves inside out when threatened, exposing spines that make them appear even more otherworldly. Deep-sea anglerfish have evolved some of the most bizarre mating strategies in nature, with tiny males permanently fusing to the bodies of much larger females, becoming nothing more than sperm-producing appendages. Barreli fish possess transparent heads that house tubular eyes capable of rotating upward to spot prey from below. When these creatures were first photographed, marine biologists weren't even sure they were looking at real animals. The images seemed too strange, too perfectly alien to be products of earthly evolution. These discoveries raise profound questions about what else might be lurking in unexplored regions of our oceans. Every deep-sea expedition reveals new species, suggesting that millions of organisms remain unknown to science. Some researchers estimate that we've catalogued less than 5% of deep-sea species, meaning vast kingdoms of life remain hidden beneath the waves. The deep sea also holds secrets about Earth's history. Sediment cores pulled from the ocean floor contain records spanning millions of years, preserving evidence of past climates, extinction events, and the gradual drift of continents. These underwater archives help us understand how our planet has changed over geological time and what we might expect as climate patterns continue to shift. Ancient shipwrecks rest preserved in the deep sea's cold, oxygen-poor environment. The famous Titanic, sitting at a depth of 3,800 meters, has become an inadvertent laboratory for studying how metal and organic materials decay in deep ocean conditions. Other vessels, some thousands of years old, rest on the seafloor in remarkable states of preservation, offering glimpses into human history that terrestrial archaeology could never provide. But the ocean floor itself tells an even older story. Mid-ocean ridges, where tectonic plates spread apart, create new seafloor in a process that has continued for billions of years. These underwater mountain ranges stretch for over 65,000 kilometers around the globe, making them the longest mountain chain on Earth. Along these ridges, volcanic activity creates new land while hydrothermal vents support unique ecosystems that might resemble life's earliest forms. The deep-sea trenches, where tectonic plates collide and one slides beneath another, represent some of the most geologically active regions on our planet. The Ring of Fire, encircling the Pacific Ocean, generates earthquakes and tsunamis that can be felt thousands of miles away. Deep-sea monitoring stations help us understand these processes, but vast regions remain unobserved, leaving us vulnerable to surprises from the depths. Mineral deposits on the deeper sea floor have attracted increasing attention as land-based resources become scarcer. Polymetallic nodules, looking like scattered potatoes on the abyssal plains, contain valuable metals, including manganese, nickel, cobalt, and rare earth elements crucial for modern electronics. These nodules form over millions of years as metals precipitate from seawater, creating what some have called underwater treasure fields. Massive sulfide deposits around hydrothermal vents contain concentrations of copper, gold, silver, and other valuable minerals far exceeding most land-based ore bodies. However, extracting these resources would require technologies that don't yet exist and might destroy unique ecosystems before we've had chance to study them properly. The deep sea also plays crucial roles in global climate regulation that we're only beginning to understand. Deep ocean currents transport heat around the planet, influencing weather patterns and regional climates. These currents, driven by differences in water temperature and salinity, move slowly but carry enormous volumes of water. The global conveyor belt of ocean circulation helps moderate Earth's climate, but climate change is already altering these patterns in ways that could have far-reaching consequences. Carbon dioxide absorbed by the ocean's surface eventually sinks to the deep sea, where it can remain stored for centuries or millennia. This natural carbon sequestration helps moderate atmospheric carbon dioxide levels, but we're unsure how much additional carbon the deep sea can absorb before reaching saturation point. Ocean acidification, caused by increased carbon dioxide absorption, is already affecting marine ecosystems, but its impacts on deep-sea environments remain largely unknown. The deep ocean also serves as a vast reservoir of nutrients that support surface marine life. Upwelling zones, where deep water rises to the surface, bring nutrients from the depths to fuel some of the world's most productive fisheries. Without this vertical mixing, the upper ocean would be a largely barren desert, unable to support the marine food webs that humans depend upon. Yet our understanding of these critical processes remains fragmentary. Ocean circulation models require data from depths that are difficult and expensive to monitor. Climate scientists work with incomplete information about how the deep sea will respond to changing conditions, making long-term predictions challenging and uncertain. The technological barriers to deep-sea exploration continue to evolve, but slowly. Robotic vehicles have extended our reach into the abyss, allowing us to explore dangerous environments without risking human lives. These remotely operated vehicles, or ROVs, can work in conditions that would destroy manned submersibles, but they're limited by their connection to surface vessels through cables that can stretch for miles. Autonomous underwater vehicles, or AUVs, operate independently for periods ranging from hours to months, collecting data and samples without direct human control. These robots have revolutionized oceanography, but they're expensive to build and operate, limiting the number of missions that can be undertaken. Battery technology, pressure resistance, and communication systems all pose ongoing challenges for extending their capabilities. Recent advances in materials science have enabled the construction of vessels capable of reaching even greater depths. The submersible limiting factor has successfully reached the deepest parts of all 5 oceans, including multiple dives to Challenger deep in the Mariana Trench. However, these achievements represent individual expeditions rather than sustained exploration programs. The cost factor cannot be overstated. A single deep-sea research vessel can cost hundreds of millions of dollars to build and millions more each year to operate. Research funding agencies must balance deep-sea exploration against other scientific priorities, often leaving vast regions unexplored for decades. Private funding has begun supplementing government research budgets, but the scale of the oceans dwarfs even the most generous private investments. International cooperation offers one path forward, but coordinating multinational research efforts presents its own challenges. Different countries have varying technological capabilities, research priorities, and regulatory frameworks. Disputes over territorial waters and mineral rights can complicate collaborative exploration efforts, particularly in regions with potential commercial value. The legal framework governing deep-sea exploration adds another layer of complexity. Waters beyond national jurisdictions fall under international law, but enforcement mechanisms remain weak. The deep seabed is considered the common heritage of mankind, yet determining who has the right to explore, extract resources, or conduct research in specific areas requires navigating complex international agreements. Environmental protection presents additional challenges. How do we study ecosystems without disturbing them? Every deep-sea expedition leaves some footprint, whether from submersible lights that might disrupt natural behaviors, sampling equipment that removes organisms from their habitat, or simple physical disturbance of seafloor sediments. Balancing scientific inquiry with ecosystem preservation requires careful consideration of research methods and long-term monitoring of study sites. The precautionary principle suggests we should move slowly and carefully as we explore these environments, but the urgency of understanding climate change and other global challenges pushes for accelerated research. This tension between caution and urgency influences research priorities and methodologies, sometimes in conflicting ways. Deep-sea mining presents the starkest example of these competing interests. The potential economic value of deep-sea mineral deposits is enormous, particularly as demand for battery materials and rare earth elements continues growing. However, we understand so little about deep-sea ecosystems that we cannot predict the environmental consequences of large-scale extraction operations. Some of the creatures living around potential mining sites exist nowhere else on Earth. Destroying their habitats could drive species to extinction before we've had opportunity to study their biology, behavior, or potential contributions to human knowledge. The deep sea's slow growth rates and stable conditions mean that recovery from disturbance might take centuries or millennia. Yet the minerals found in deep-sea environments could be crucial for transitioning to renewable energy systems that might help address climate change. This creates an environmental paradox, potentially damaging deep-sea ecosystems to obtain materials needed to protect other ecosystems from climate change impacts. The debate over deep-sea mining has intensified as several countries and companies prepare for commercial extraction operations. International regulatory frameworks are still being developed, creating uncertainty about environmental standards and oversight mechanisms. Some scientists argue for moratoriums on deep-sea mining until we better understand these ecosystems, while others contend that carefully managed extraction could proceed with minimal environmental impact. These discussions highlight how much we still don't know about the deep sea. Our ignorance extends beyond individual species to entire ecosystem processes and relationships. How do nutrients cycle through deep-sea food webs? How do populations respond to environmental changes? How connected are different deep-sea regions? These fundamental questions remain largely unanswered. The discovery of new deep-sea ecosystems continues at a remarkable pace. Nearly every expedition to previously unexplored regions reveals new species and often entirely new communities of organisms. The Yeti crab, discovered in 2005, lives near hydrothermal vents and cultivates bacteria on its hairy claws for food. Glass sponge reefs off the coast of British Columbia were thought extinct for millions of years until living examples were found in the 1980s, creating underwater forests that stretch for miles. Whale falls, the carcasses of large whales that sink to the sea floor, create island ecosystems that can persist for decades. These nutrient-rich environments support unique communities of organisms, many found nowhere else. The stages of whale fall decomposition create different habitats over time, supporting different species assemblages in a predictable succession. Cold seeps, where hydrocarbons leak from the seafloor, support ecosystems similar to hydrothermal vents, but powered by different chemical processes. These seeps can persist for much longer than individual vents, creating stable environments where evolution can produce highly specialized organisms. Tube worms living around cold seeps can reach enormous sizes and ages, with some specimens estimated to be over 300 years old. Seamounts, underwater mountains that rise from the deep sea floor, create unique habitats that attract diverse marine life. These geological features alter ocean currents, creating upwelling zones that bring nutrients to their slopes and summits. Many seamounts support endemic species found nowhere else, making each one a unique ecosystem worthy of individual study. The number of seamounts in the world's oceans remains unknown, with estimates ranging from 30,000 to over 100,000. Most have never been explored, and many haven't even been mapped in detail. Each represents a potential laboratory for understanding evolution, biogeography, and deep-sea ecology. Underwater canyons carve dramatic landscapes into continental margins, channeling sediment and nutrients from shallow water to the deep sea. These canyons create diverse habitats within relatively small areas, supporting everything from filter-feeding communities on canyon walls to predator species that hunt in canyon currents. The Monterey Canyon off California rivals the Grand Canyon in size and contains ecosystems found nowhere else on Earth. Abyssal plains, the vast flat regions of the deep sea floor, might appear barren from a distance, but actually support diverse communities of organisms adapted to life in fine sediments. Xenophyophores, giant single-celled organisms that can grow larger than softballs, create three-dimensional structures that provide habitat for small organisms. Sea pigs, specialized sea cucumbers, roam the abyssal plains in herds, processing sediment and recycling nutrients. Even the water column of the deep sea harbors mysteries. The deep scattering layer, detected by early sonar systems, was initially thought to be a false bottom. Scientists eventually discovered this acoustic signature comes from massive aggregations of small organisms that migrate vertically through the water column each day. This daily migration, involving billions of small fish, squid, and crustaceans, represents the largest animal migration on Earth. Bioluminescence reaches its peak diversity in the deep sea, where organisms have evolved dozens of different ways to produce light. Some creatures use light to attract prey, others to communicate with potential mates, and still others to confuse predators. The chemical mechanisms behind bioluminescence vary widely between species, suggesting that the ability to produce light evolved independently many times in deep-sea environments. Deep-sea jellies showcase some of the most spectacular examples of bioluminescence. Atolla jellyfish create spinning wheels of light when threatened, perhaps to attract the attention of predators that might attack whatever is threatening the jelly. Barrel jellyfish pulse with waves of blue light as they drift through the water column. Some deep-sea siphonophores, colonial organisms related to jellyfish, can stretch longer than blue whales, while remaining thinner than a human hair. The study of deep-sea bioluminescence has contributed to numerous scientific and medical advances. The green fluorescent protein, originally isolated from deep-sea jellyfish, has become an essential tool in molecular biology, allowing researchers to track cellular processes in real time. Other bioluminescent compounds from deep-sea organisms have been developed into sensitive assays for detecting cellular activity, environmental contamination, and disease markers. Yet we've barely begun to catalogue the diversity of bioluminescent organisms in the deep sea, let alone understand the ecological significance of their light production. How do organisms distinguish between different types of bioluminescent signals? How has the evolution of light production influenced predator-prey relationships? How might artificial light pollution from human activities affect natural bioluminescent communication? These questions become more urgent as human activities increasingly impact deep-sea environments. Deep-sea fishing operations use powerful lights that might disrupt natural behaviors in species that have evolved in absolute darkness. Underwater cables carrying internet and telephone signals crisscross the ocean floor, potentially affecting organisms that rely on electrical or magnetic cues for navigation or communication. Pollution from surface sources eventually finds its way to the deep sea, where it can persist for much longer than in more dynamic surface environments. Plastic debris has been found in the deepest ocean trenches, and toxic chemicals accumulate in deep-sea organisms that have no evolutionary experience with such compounds. The long lifespans and slow metabolisms of many deep-sea species make them particularly vulnerable to contamination. Climate change presents perhaps the greatest long-term challenge to deep-sea ecosystems. As surface waters warm, the temperature difference that drives deep ocean circulation could weaken, potentially disrupting current systems that have remained stable for thousands of years. Changes in ocean chemistry, including acidification and decreasing oxygen levels, could fundamentally alter the conditions that deep-sea organisms depend upon. Ocean warming, even in the deep sea where temperature changes occur slowly, could trigger cascading effects throughout deep-sea food webs. Species adapted to narrow temperature ranges might face extinction if they cannot migrate to more suitable habitats. The slow pace of reproduction and development in many deep-sea species means that populations might not be able to adapt quickly enough to changing conditions. The oxygenation of the deep sea has already been detected in some regions, creating expanding dead zones where most organisms cannot survive. These oxygen minimum zones could grow larger as climate change continues, potentially eliminating vast areas of deep-sea habitat. The organisms that remain might be quite different from those that currently inhabit these regions, with unknown consequences for ecosystem functioning. Despite these challenges, the deep sea continues to surprise us with its resilience and adaptability. Life has persisted in deep-sea environments for billions of years, surviving mass extinctions and dramatic environmental changes. The stability that characterizes much of the deep sea has allowed evolution to produce some of the most specialized and remarkable organisms on Earth. Understanding these adaptations could inform human efforts to survive in extreme environments, whether in the deep sea itself or in space. The proteins that allow deep-sea organisms to function under extreme pressure might have applications in biotechnology or medicine. The energy-efficient metabolisms of deep-sea creatures could inspire new approaches to engineering and design. The deep sea also offers insights into the fundamental processes that govern life on Earth. The chemosynthetic ecosystems around hydrothermal vents provide models for how life might have originated on our planet billions of years ago. The extreme longevity of some deep-sea organisms raises questions about the biological limits of aging and the genetic mechanisms that control lifespan. Studying deep-sea environments might also help us understand the potential for life on other worlds. The moons Europa and Enceladus, orbiting Jupiter and Saturn respectively, are thought to harbor deep oceans beneath their icy surfaces. The conditions in these alien seas might resemble those in Earth's deep ocean, suggesting that similar forms of life could exist elsewhere in our solar system. The technologies developed for deep-sea exploration have applications far beyond marine science. Pressure-resistant materials, autonomous navigation systems, and remote sensing technologies, originally designed for ocean research, have found uses in aerospace, medicine, and industry. The challenges of operating in the deep sea parallel those of working in space, making deep-sea technology development relevant to future space exploration efforts. As we continue to explore Earth's oceans, each expedition reveals how much more there is to discover. The deep sea remains our planet's final frontier, a realm where new species await discovery and fundamental questions about life, evolution, and planetary processes remain unanswered. The technological challenges that have limited our exploration of these environments are gradually being overcome, but the scale of the oceans ensures that mysteries will persist for generations to come. The economic argument for deep-sea exploration grows stronger as terrestrial resources become scarcer and more expensive to extract. The deep sea contains vast quantities of materials essential for modern technology, from rare earth elements needed for electronics to metals required for renewable energy systems. However, accessing these resources sustainably will require much better understanding of deep-sea ecosystems and the development of extraction technologies that minimize environmental impact. The scientific argument for deep-sea exploration is equally compelling. The deep sea represents the largest habitat on Earth, yet we know less about it than we know about the surface of Mars. This vast realm undoubtedly harbors discoveries that could revolutionize our understanding of biology, geology, chemistry, and climate science. The potential for finding new medicines, understanding new biological processes, and discovering new principles that could advance human knowledge makes deep-sea exploration one of the most promising frontiers for scientific research. The cultural and philosophical significance of the deep sea should not be overlooked. These hidden realms challenge our understanding of what is possible on our planet and expand our conception of the conditions under which life can thrive. The deep sea reminds us that Earth still holds secrets and that the age of exploration is far from over. In an era when many feel that everything has been discovered and mapped, the deep sea offers genuine mystery and the possibility of profound surprises. The aesthetic beauty of deep-sea environments, revealed through advances in underwater photography and videography, has begun to capture public imagination in ways that could support increased exploration efforts. Images of bioluminescent jellyfish, towering hydrothermal vent chimneys, and bizarre deep-sea creatures have found their way into art, literature, and popular culture, helping to build appreciation for these hidden worlds. Educational institutions are increasingly recognizing the importance of ocean literacy and the role of the deep sea in Earth systems. New curricula emphasize the connections between deep sea processes and surface phenomena that directly affect human societies. Understanding these connections is crucial for making informed decisions about resource use, environmental protection, and climate change adaptation. The next generation of deep-sea explorers will have access to technologies that current researchers can only dream of. Advances in robotics, artificial intelligence, materials science, and energy storage will enable longer, deeper, and more comprehensive exploration of deep-sea environments. Swarms of small, inexpensive robots might replace the large, costly submersibles currently used for deep-sea research, making exploration more affordable and accessible. Satellite technology and surface-based sensors are already providing new ways to study the deep sea without actually going there. Gravitational measurements can detect underwater mountains and valleys, while changes in sea surface temperature and color can reveal deep water upwelling events. These remote sensing approaches complement direct exploration, helping scientists identify the most interesting and important areas for detailed study. International cooperation in deep-sea research is likely to increase as the costs and complexities of exploration encourage shared efforts. Large-scale research programs involving multiple countries and institutions can tackle questions that would be impossible for any single organization to address. The success of international collaborations in space exploration provides models for similar efforts in the deep sea. Private sector involvement in deep sea exploration is expanding as commercial opportunities become clearer. Companies developing deep sea mining technologies are investing in research and exploration, while tourism operators are beginning to offer deep sea experiences to wealthy adventurers. This commercial interest could accelerate the pace of exploration and discovery, though it also raises concerns about environmental protection and equitable access to deep-sea resources. The integration of big data approaches and machine learning into deep-sea research is revealing patterns and connections that would be impossible to detect through traditional analysis methods. Large datasets collected by autonomous vehicles and sensor networks can be analyzed by artificial intelligence systems to identify new species, predict the locations of mineral deposits, or model ecosystem responses to environmental changes. Citizen science initiatives are beginning to extend into deep-sea research, allowing members of the public to contribute to exploration and discovery efforts. Online platforms enable volunteers to analyze images and video collected by deep-sea expeditions, helping to catalog species and document behaviors. These efforts not only advance scientific understanding, but also build public engagement with deep-sea exploration. The philosophical questions raised by deep-sea exploration touch on fundamental issues about humanity's relationship with nature and our responsibilities as planetary stewards. The deep sea challenges anthropocentric views of Earth by revealing vast realms where humans have never been and ecosystems that function independently of surface processes. This perspective could influence how we think about environmental protection, resource use, and our place in the natural world. The deep sea also raises questions about the ethics of exploration and exploitation. Do we have the right to disturb environments that have remained unchanged for millions of years? How do we balance the potential benefits of deep-sea resources against the risks of environmental damage? How do we ensure that the benefits of deep-sea exploration are shared equitably among all nations and peoples? These ethical considerations become more complex when we consider the global nature of deep-sea environments and the long time scales over which deep-sea processes operate. Decisions made today about deep-sea exploration and exploitation will have consequences that persist for centuries or millennia. The deep sea forces us to think beyond immediate interests and consider our legacy for future generations. The deep sea continues to inspire artists, writers, and filmmakers who find in its mysteries and beauty sources of creativity and wonder. Science fiction authors have long used deep-sea environments as settings for stories about alien contact, technological innovation, and human adaptation to extreme conditions. Documentary filmmakers have brought the beauty and strangeness of deep-sea life to audiences who would never otherwise experience these environments. This cultural impact of deep-sea exploration extends beyond entertainment to influence how we think about possibility, adaptation, and the limits of life. The extreme organisms of the deep sea challenge our assumptions about what is normal or natural, encouraging more flexible and creative thinking about biological and technological solutions to human challenges. The deep sea serves as a laboratory for studying basic principles that govern all of life. The extreme conditions found in deep-sea environments test the limits of biological systems and reveal fundamental constraints on living processes. Understanding how organisms function under extreme pressure, in complete darkness, at freezing temperatures, and with limited food sources, provides insights into the basic mechanics of life that apply to organisms in all environments. The isolation of many deep-sea habitats makes them natural experiments in evolution and biogeography. Islands of habitat, separated by vast expanses of inhospitable seafloor, allow scientists to study how populations diverge and new species arise. The patterns of species distribution in the deep sea inform our understanding of evolution, dispersal, and the factors that promote or limit biodiversity. Deep sea research contributes to our understanding of Earth history and the processes that have shaped our planet over geological time. Sediment cores from the deep ocean provide records of past climates, ocean chemistry, and biological productivity that extend back millions of years. These records help us understand natural variability in Earth systems and place current environmental changes in historical context. The deep sea also preserves evidence of catastrophic events that have shaped the course of evolution. Impact craters from asteroid collisions, evidence of massive volcanic eruptions, and signatures of rapid climate changes are all preserved in deep-sea sediments. This geological archive helps us understand how ecosystems respond to sudden environmental changes and how long recovery takes. The mineral deposits found in deep-sea environments provide clues about the chemical evolution of our planet and the processes that concentrate valuable elements in economically viable deposits. Understanding how these deposits form could help us locate similar resources on land and develop more efficient extraction and processing technologies. The study of deep-sea hydrothermal systems has revolutionized our understanding of the role of water in geological processes and the cycling of elements between Earth's interior and surface environments. These systems demonstrate how geological and biological processes interact to create and maintain the conditions that support life on our planet. Deep-sea exploration has practical applications for understanding and predicting natural hazards that affect human societies. Underwater landslides, earthquake-triggered tsunamis, and volcanic eruptions all originate in deep-sea environments and can cause devastating damage to coastal communities. Monitoring systems deployed in the deep sea provide early warning of these hazards and help scientists understand the processes that trigger them. The deep sea plays a crucial role in global fisheries. Even though most commercially important species live in shallower waters, many fish species spend parts of their life cycles in deep water, and the nutrients and plankton produced in deep sea environments ultimately support surface marine food webs. Understanding these connections is essential for managing fisheries sustainably and predicting how fish populations might respond to environmental changes. Climate models used to predict future environmental conditions require accurate information about deep-sea processes, including ocean circulation, heat transport, and carbon cycling. Improvements in our understanding of deep-sea systems translate directly into more reliable predictions of climate change impacts and more informed policy decisions about climate change mitigation and adaptation. The deep sea offers opportunities for developing new technologies that could have broad applications in human society. The extreme conditions found in deep sea environments push engineering systems to their limits and encourage innovative solutions that often find uses in other challenging environments. Robotics, materials, science, energy systems, and communication technologies all benefit from advances driven by deep sea exploration needs. Biotechnology applications of deep-sea research continue to expand as we discover new organisms with unique biochemical capabilities, enzymes that function under extreme pressure and temperature, proteins that resist degradation, and metabolic pathways that operate with high efficiency, all have potential applications in industry, medicine, and environmental remediation. The pharmaceutical industry has shown increasing interest in deep-sea organisms as sources of new drugs and therapeutic compounds. The unique evolutionary pressures of deep-sea environments have produced novel biochemical compounds that might have applications in treating human diseases. However, the slow growth rates and small population sizes of many deep-sea organisms make sustainable harvesting of these resources challenging. Conservation of deep-sea environments presents unique challenges that differ significantly from terrestrial or shallow marine conservation efforts. The vast scales of deep-sea habitats, the difficulty of monitoring remote areas, and the long timescales over which deep-sea processes operate all complicate traditional conservation approaches. New strategies are needed that account for the special characteristics of deep-sea ecosystems. International coordination is essential for effective deep-sea conservation, since most deep-sea environments lie beyond national jurisdictions, and many species have wide distributions that cross political boundaries. The development of international agreements for deep-sea conservation is complicated by competing national interests, different levels of technological capability, and disagreements about the appropriate balance between conservation and economic development. The precautionary principle suggests that we should err on the side of caution when making decisions about deep-sea environments, given our limited understanding of these systems and the potentially irreversible nature of some human impacts. However, applying this principle in practice requires difficult decisions about acceptable levels of risk and uncertainty, especially when potential benefits are large and immediate, while risks are uncertain and long-term. Adaptive management approaches, which allow for adjustment of conservation strategies as new information becomes available, offer promise for deep-sea conservation. These approaches recognize that our understanding of deep-sea systems will continue to evolve, and that conservation strategies need to be flexible enough to incorporate new knowledge and respond to changing conditions. The deep sea provides natural laboratories for studying fundamental questions in ecology, evolution, and environmental science. The extreme conditions and isolation of many deep-sea habitats make them ideal systems for testing ecological theories and understanding how environmental factors influence biological processes. Research in these natural laboratories contributes to our understanding of how ecosystems function and how they respond to environmental changes. Comparative studies between different deep-sea environments reveal general principles about life in extreme conditions and the factors that promote or limit biodiversity. Hydrothermal vents, cold seeps, whale falls, and other specialized deep-sea habitats each offer unique insights into how organisms adapt to challenging conditions and how communities assemble and persist over time. The deep sea challenges traditional concepts in ecology and evolution by presenting organisms with environmental conditions unlike those found anywhere else on Earth. Studying how life has adapted to these extreme conditions expands our understanding of what is biologically possible and provides insights into the flexibility and limits of evolutionary processes. Long-term studies of deep-sea environments are beginning to reveal patterns of change and stability that operate on timescales much longer than most ecological research. These studies provide baselines for understanding natural variability and detecting human impacts, but they require sustained funding commitments and international cooperation to maintain monitoring programs over the decades or centuries needed to capture important patterns. The technological demands of deep-sea research continue to drive innovations that benefit other fields of science and engineering. Pressure-resistant electronics, efficient life support systems, autonomous navigation, and remote manipulation technologies all have applications beyond deep-sea research. The engineering challenges posed by the deep-sea environment stimulate creative solutions that often find unexpected uses in other contexts. Communication systems for deep-sea operations must overcome the challenge of transmitting information through seawater, which absorbs electromagnetic radiation and limits the range of traditional radio communications. Acoustic communication systems, fiber optic cables, and other technologies developed for deep-sea use have influenced communication system design for other challenging environments. Power systems for deep-sea operations must be highly reliable and efficient, since equipment failures in remote deep-sea environments can be catastrophic. Advances in battery technology, fuel cells, and energy harvesting systems, driven by deep-sea exploration needs, benefit portable electronics, electric vehicles, and renewable energy systems used on land. The materials science challenges of deep-sea exploration have led to advances in high-strength composites, corrosion-resistant alloys, and pressure-resistant seals that find applications in aerospace, automotive, and other industries. The extreme conditions of the deep-sea test materials to their limits and reveal failure modes that might not be apparent in less demanding applications. Navigation and positioning systems for deep-sea operations cannot rely on GPS signals which do not penetrate seawater effectively. Inertial navigation, acoustic positioning, and other technologies developed for deep-sea use have applications in underground mining, tunnel construction, and other environments where satellite navigation is unavailable. The psychological challenges of deep-sea exploration mirror those faced by astronauts and other explorers working in extreme isolation. The confined spaces of submersibles, the stress of operating in dangerous environments, and the separation from normal human social contact all place unique demands on expedition members. Understanding and managing these psychological factors is crucial for the success and safety of deep-sea missions. Training programs for deep-sea explorers incorporate lessons learned from space exploration, military operations, and polar research about how to select and prepare individuals for extreme environments. These programs must address not only technical skills, but also psychological resilience, teamwork abilities, and decision-making under stress. The economic challenges of deep-sea exploration create barriers that limit research progress and delay important discoveries. The high costs of specialized equipment, the need for extensive support operations, and the risks associated with working in extreme environments all contribute to making deep-sea research one of the most expensive forms of scientific investigation. Funding agencies must balance the potential scientific and economic benefits of deep-sea research against competing demands for limited resources. The long timescales required for deep-sea research projects, often spanning decades from initial planning to final results, complicate traditional funding cycles and require sustained institutional commitments that can be difficult to maintain. Public-private partnerships offer one approach to overcoming funding limitations by combining government resources with commercial investments. However, these partnerships require careful structuring to ensure that scientific objectives are not compromised by commercial interests and that environmental protection remains a priority. Crowdfunding and other novel financing mechanisms have begun to supplement traditional funding sources for some deep-sea research projects. These approaches can generate public interest and support for deep-sea exploration while providing alternative sources of funding, though they are typically suitable only for smaller-scale projects. The educational value of deep-sea exploration extends far beyond marine science to encompass physics, chemistry, geology, biology, engineering, and other disciplines. Deep-sea environments provide compelling examples of extreme conditions, adaptation strategies, and technological solutions that can capture student interest and illustrate important scientific principles. Virtual reality and other immersive technologies are beginning to bring deep-sea experiences to classrooms and museums, allowing students to explore environments they could never visit in person. These educational tools help build ocean literacy and inspire the next generation of scientists, engineers, and conservationists. Hands-on educational programs that involve students in analyzing deep-sea data, designing exploration equipment, or participating in research expeditions provide valuable learning experiences while contributing to scientific research. These programs demonstrate the relevance of academic subjects to real-world challenges and career opportunities. The integration of deep-sea content into popular media, from nature documentaries to science fiction films, helps build public awareness and support for ocean exploration. Well-produced media content can convey the beauty, mystery, and importance of deep-sea environments to audiences who might otherwise have little interest in marine science. Social media platforms provide new opportunities for deep-sea researchers to share their discoveries and experiences with global audiences in real time. Live streaming from research vessels, underwater photography, and behind-the-scenes content from expeditions help demystify scientific research and build connections between researchers and the public. The global nature of deep-sea environments creates opportunities for international scientific collaboration on a scale rarely seen in other fields. Research projects that span multiple oceans and involve scientists from dozens of countries can address questions that no single nation could tackle alone. Data sharing initiatives in deep-sea research are creating global databases that make research results more accessible and useful to the broader scientific community. These initiatives require standardization of data collection methods, development of common data formats, and agreement on data sharing protocols that balance open access with legitimate commercial and national security interests. Capacity building programs help developing nations participate in deep-sea research and benefit from the knowledge and resources that exploration efforts generate. These programs transfer technology, train scientists and technicians, and support the development of research infrastructure in countries that lack the resources to mount independent deep-sea exploration efforts. The legal and regulatory framework governing deep-sea activities continues to evolve as new technologies make previously inaccessible areas exploitable and new environmental concerns emerge. International law of the sea treaties, environmental protection agreements, and bilateral cooperation arrangements all influence how deep-sea exploration and exploitation can proceed. Dispute resolution mechanisms for deep-sea activities must address conflicts between nations with different interpretations of their rights and responsibilities in international waters. These mechanisms must be able to handle technical disputes about environmental impacts, resource extraction rights, and scientific research priorities. The enforcement of deep-sea regulations presents significant practical challenges due to the remote locations involved and the difficulty of monitoring activities in deep water. Satellite surveillance, automatic identification systems, and other monitoring technologies can help track vessel activities, but verifying compliance with detailed environmental or safety regulations requires more intensive oversight. Liability issues for deep-sea activities raise complex questions about responsibility for environmental damage, accidents involving research personnel, and interference with other users of ocean resources. Insurance mechanisms, compensation funds, and international liability treaties all play roles in managing these risks. The cultural heritage aspects of deep-sea exploration include not only shipwrecks and other archaeological sites, but also the traditional knowledge that indigenous communities have developed about ocean environments. Incorporating this traditional knowledge into modern research efforts can provide valuable insights while respecting the rights and contributions of indigenous peoples. Sacred sites and culturally significant areas in marine environments require special consideration in deep-sea exploration and exploitation activities. Consultation with affected communities, development of appropriate protection measures, and recognition of cultural values alongside scientific and economic interests are essential for responsible deep-sea activities. The representation of different nations, cultures, and perspectives in deep-sea research helps ensure that exploration efforts reflect global interests rather than just the priorities of wealthy nations with advanced marine technologies. Achieving this representation requires deliberate efforts to include researchers from diverse backgrounds and support their participation in international research programs. Gender equality in deep-sea research remains a challenge, with women underrepresented in many aspects of ocean exploration, from research leadership to technical operations. Addressing this imbalance requires examining and changing practices that create barriers to women's participation, from fieldwork logistics to career advancement opportunities. The interdisciplinary nature of deep-sea research creates opportunities for collaboration across traditional academic boundaries, while also presenting challenges for researchers trained in specialized disciplines. Successful deep-sea research teams often include biologists, geologists, chemists, engineers, and other specialists who must learn to communicate effectively across disciplinary boundaries. Training programs for deep-sea researchers must prepare scientists to work in interdisciplinary teams, operate complex technical equipment, and adapt to rapidly changing field conditions. These programs often combine traditional academic training with hands-on experience in marine operations, technical skills development, and leadership training. Career paths in deep-sea research are often non-linear and may require geographic mobility, extended periods at sea, and flexibility in research focus as funding opportunities and scientific priorities change. Supporting diverse career paths in deep-sea research requires mentorship programs, professional development opportunities, and institutional policies that recognize the unique demands of ocean research careers. The work-life balance challenges faced by deep-sea researchers, including extended separations from family during research expeditions and irregular work schedules driven by weather and equipment availability, require supportive institutional policies and understanding from employers and family members. The health and safety considerations for deep-sea research extend beyond the obvious risks of working in marine environments to include psychological stress, exposure to unusual atmospheric conditions in submersibles, and the medical challenges of providing healthcare in remote locations far from advanced medical facilities. Emergency response planning for deep-sea operations must account for the limited options available for rescue and medical evacuation in remote ocean areas. Coordination with military and commercial vessel traffic, pre-positioned emergency equipment, and detailed contingency plans are all essential for managing the risks inherent in deep-sea operations. The environmental footprint of deep-sea research, including fuel consumption by research vessels, waste generation during extended expeditions, and the physical impact of sampling and observation equipment on seafloor environments, requires careful management to minimize research impacts on the environments being studied. Sustainable research practices in deep-sea environments include minimizing physical disturbance, using non-invasive observation methods when possible, and coordinating multiple research objectives within single expeditions to reduce the total number of visits to sensitive areas. The long-term monitoring requirements for understanding deep-sea ecosystem changes present logistical and financial challenges that exceed the capabilities of most individual research projects. Establishing sustainable monitoring programs requires institutional commitments that span decades and coordination among multiple funding agencies and research organizations. Technological innovation in deep-sea monitoring is beginning to provide new options for long-term data collection, including autonomous sensor networks, satellite-linked communication systems, and low-power instruments that can operate for years without maintenance. However, these technologies require significant upfront investments and ongoing support for data management and analysis. The integration of deep-sea research with global Earth observation systems helps place deep-sea discoveries in the context of planetary-scale processes and changes. This integration requires standardization of data formats, coordination of observation schedules, and development of analysis tools that can handle data from multiple sources and platforms. Climate change impacts on deep-sea research include changes in weather patterns that affect research vessel operations, shifting ocean conditions that alter the environments being studied, and evolving research priorities as society's understanding of climate change impacts develops. The role of deep-sea environments in climate regulation makes deep-sea research increasingly relevant to climate change mitigation and adaptation strategies. Understanding how deep-sea processes affect global climate systems informs policy decisions about greenhouse gas emissions, climate engineering approaches, and adaptation planning for coastal communities. Ocean acidification. One of the most direct impacts of increased atmospheric carbon dioxide on marine environments affects deep-sea organisms and ecosystems in ways that are only beginning to be understood. Research on ocean acidification impacts requires long-term studies and careful attention to natural variability in ocean chemistry. The changing chemistry of seawater due to human activities affects not only biological processes but also geological processes such as mineral formation and dissolution. These chemical changes could alter the formation of deep-sea mineral deposits and affect the stability of seafloor sediments. Deep-sea carbon sequestration processes, including the burial of organic matter in seafloor sediments and the formation of methane hydrates, play important roles in global carbon cycling, but are vulnerable to disruption by climate change and human activities. The potential for engineering deep-sea environments to enhance carbon sequestration raises both opportunities and concerns about large-scale intervention in natural systems. Research on these approaches must carefully consider unintended consequences and ethical implications alongside technical feasibility. Methane hydrates, ice-like compounds that trap large quantities of methane in seafloor sediments, represent both a potential energy resource and a climate change concern. Understanding the stability and distribution of these compounds is crucial for assessing their role in future energy systems and climate change scenarios. The deep-sea microbial communities that mediate many important chemical processes remain poorly understood, despite their critical roles in global biogeochemical cycles. These microorganisms process carbon, nitrogen, sulfur, and other elements in ways that affect ocean chemistry and global climate. Genomic approaches to studying deep-sea microbial communities are revealing the incredible diversity of metabolic strategies that microorganisms use to survive in extreme deep-sea conditions. This research provides insights into the evolutionary origins of life and the potential for life in other extreme environments. The symbiotic relationships between deep-sea organisms and their microbial partners often involve metabolic processes that are unknown in surface environments. Understanding these relationships could lead to new biotechnological applications and insights into the evolution of complex biological systems. Horizontal gene transfer, the movement of genetic material between different species of microorganisms, appears to be particularly important in deep-sea environments where organisms face extreme selective pressures. This process allows rapid adaptation to changing conditions and contributes to the genetic diversity of deep-sea microbial communities. The discovery of new metabolic pathways in deep-sea microorganisms continues to expand our understanding of the biochemical possibilities for life. These discoveries have implications for understanding the limits of life on Earth and the potential for life elsewhere in the universe. Deep-sea viruses, which are abundant but poorly studied, play important roles in controlling microbial populations and mediating genetic exchange between different microorganisms. Understanding viral ecology in deep-sea environments could provide insights into the factors that control microbial diversity and ecosystem functioning. The food webs of deep-sea environments are often more complex than they initially appear, with multiple energy sources and intricate relationships between organisms at different trophic levels. Understanding these food web dynamics is essential for predicting how deep-sea ecosystems will respond to environmental changes. Stable isotope analysis and other biochemical techniques are revealing unexpected connections between different deep-sea habitats and between deep-sea and surface environments. These connections suggest that deep-sea ecosystems are more integrated with global ocean systems than previously recognized. The role of large predators in deep-sea ecosystems remains poorly understood, partly because these animals are difficult to observe and study in their natural habitats. However, evidence suggests that top predators play important roles in structuring deep-sea communities and connecting different habitats through their movements and feeding behaviors. Migration patterns of deep-sea organisms, including daily vertical migrations and seasonal movements, create connections between different ocean layers and regions that are important for nutrient cycling and energy transfer. Understanding these patterns requires long-term tracking studies and coordination between research groups studying different areas. The reproductive strategies of deep-sea organisms often involve adaptations to the challenges of finding mates in vast, sparsely populated environments. These strategies include bioluminescent displays, chemical signaling, and unusual mating systems that maximize reproductive success under extreme conditions. Larval dispersal in deep-sea environments can connect populations separated by thousands of kilometers, but the mechanisms controlling this dispersal and the factors determining where larvae successfully settle remain poorly understood. This knowledge gap makes it difficult to predict how deep-sea populations will respond to environmental changes or human impacts. The genetic diversity of deep-sea populations reflects their evolutionary history and their potential for adapting to environmental changes. However, assessing this diversity requires extensive sampling and genetic analysis that is expensive and logistically challenging in deep-sea environments. Conservation genetics approaches are beginning to inform deep-sea conservation strategies by identifying genetically distinct populations, understanding patterns of gene flow between populations, and assessing the genetic health of threatened species. This information is crucial for designing effective protected areas and management strategies. The connectivity between different deep-sea regions affects how local disturbances spread and how damaged ecosystems recover. Understanding these connectivity patterns requires regional-scale research programs and coordination between research groups studying different areas. Marine protected areas in deep-sea environments face unique challenges due to the vast scales involved, the difficulty of enforcement in remote areas, and the limited knowledge available about the ecosystems being protected. Designing effective deep-sea protected areas requires careful consideration of biological, physical, and human factors. The effectiveness of different conservation strategies in deep-sea environments remains largely untested due to the short history of deep-sea conservation efforts and the long timescales over which deep-sea ecosystems respond to protection measures. Adaptive management approaches that allow for adjustment of conservation strategies based on monitoring results offer promise for improving conservation effectiveness. Restoration of damaged deep-sea environments presents enormous technical and logistical challenges due to the extreme conditions involved and the slow pace of natural recovery processes. However, research on restoration techniques could provide valuable tools for mitigating the impacts of human activities on deep-sea ecosystems. The cumulative impacts of multiple human activities on deep-sea environments are difficult to assess and predict due to the complexity of these systems and the interactions between different types of disturbance. Understanding cumulative impacts requires integrated research approaches that consider multiple stressors simultaneously. Ecosystem-based management approaches for deep-sea environments attempt to consider entire ecosystems rather than individual species or resources in isolation. These approaches require comprehensive understanding of ecosystem structure and function, which is still developing for most deep-sea environments. The precautionary principle in deep-sea management suggests erring on the side of caution when making decisions about activities that could harm poorly understood ecosystems. However, applying this principle requires difficult judgments about acceptable levels of risk and uncertainty, especially when potential benefits are large and immediate. Stakeholder engagement in deep-sea governance involves balancing the interests of researchers, conservation organizations, commercial enterprises, and nations with different perspectives on how deep-sea resources should be used. Effective engagement requires transparent decision-making processes and mechanisms for incorporating diverse viewpoints. The traditional knowledge of seafaring peoples about deep ocean environments, while focused primarily on surface waters, sometimes includes observations and insights relevant to deep-sea research. Incorporating this knowledge into modern research efforts can provide valuable perspectives and build support for research programs in local communities. Indigenous rights in marine environments, including traditional fishing grounds and culturally significant areas that may extend into deep waters, require consideration in deep-sea exploration and exploitation planning. Consultation with indigenous communities and recognition of their rights and interests are essential for responsible deep-sea development. The economic valuation of deep-sea ecosystem services, including climate regulation, carbon sequestration, and biodiversity maintenance, is beginning to inform policy decisions about deep-sea conservation and development. However, quantifying these services and assigning economic values to them remains challenging and controversial. Market mechanisms for deep-sea conservation, including payments for ecosystem services and biodiversity credits, offer potential tools for funding conservation efforts and creating economic incentives for sustainable use of deep-sea resources. However, developing these mechanisms requires careful attention to measurement, verification, and enforcement challenges. The insurance industry's role in deep-sea activities is becoming increasingly important as the scale and value of deep-sea operations grow. Insurance requirements can influence safety practices, environmental protection measures, and risk management strategies for deep-sea activities. Liability and compensation systems for deep-sea environmental damage must address the challenges of proving causation, quantifying damages, and ensuring adequate resources are available for cleanup and restoration efforts. These systems must balance the need to hold polluters accountable with the practical challenges of operating in remote extreme environments. The international trade implications of deep-sea resources include questions about how benefits should be shared among nations, how to prevent unfair competition based on different environmental standards, and how to ensure that resource extraction contributes to sustainable development goals. Technology transfer for deep-sea capabilities raises questions about intellectual property rights, national security concerns, and equitable access to the benefits of technological advances. Balancing these competing interests requires careful consideration of both commercial and public policy objectives. The workforce development needs for expanding deep-sea industries include technical training programs, safety certification systems, and career development pathways that can attract and retain skilled workers for challenging and specialized occupations. Public perception of deep-sea activities influences political support for research funding, environmental regulations, and commercial development projects. Building public understanding and support requires effective science communication, transparent decision-making processes, and attention to public concerns about environmental protection and equitable benefit sharing. The media's role in shaping public perception of deep-sea environments through documentaries, news coverage, and entertainment programming affects public support for exploration efforts and conservation measures. Responsible media coverage that accurately represents both the opportunities and risks associated with deep-sea activities is essential for informed public discourse. Social media platforms provide new opportunities for deep-sea researchers and conservationists to engage directly with public audiences, share discoveries and experiences, and build support for their work. However, these platforms also create challenges for maintaining scientific accuracy and managing public expectations about research timelines and outcomes. The cultural impact of deep-sea discoveries extends beyond scientific communities to influence art, literature, philosophy, and popular culture. Images and stories from the deep-sea challenge our understanding of life's possibilities and our place in the natural world. Science fiction has long drawn inspiration from deep-sea environments, using them as settings for stories about alien contact, technological innovation, and human adaptation to extreme conditions. These fictional representations influence public perception of deep-sea exploration and may inspire future researchers and explorers. Artistic interpretations of deep-sea environments, from photography and videography to music and visual arts, help convey the beauty and mystery of these hidden worlds to audiences who might not otherwise appreciate their significance. Art can communicate emotional and aesthetic dimensions of deep-sea environments that scientific descriptions alone cannot capture. The philosophical implications of deep-sea exploration touch on fundamental questions about humanity's relationship with nature, the ethics of exploration and exploitation, and our responsibilities to future generations. The deep sea challenges anthropocentric worldviews and encourages more humble and respectful attitudes toward the natural world. Religious and spiritual perspectives on deep sea environments vary widely, but often emphasize themes of mystery, creation, and stewardship that resonate with conservation messages. Engaging with diverse spiritual traditions can broaden support for deep sea protection and provide additional frameworks for thinking about human obligations toward ocean environments. The psychological impact of deep-sea imagery and discoveries on individual people can be profound, evoking feelings of wonder, humility, fear, and connection with the natural world. Understanding these psychological responses can inform education programs and communication strategies for deep-sea research and conservation. Therapeutic applications of deep-sea imagery and sounds, including their use in stress reduction, meditation practices, and nature-based healing approaches, represent an unexpected benefit of deep-sea exploration efforts. The calming effects of underwater sounds and imagery have found applications in healthcare settings and personal wellness practices. The deep sea continues to inspire technological innovation that extends far beyond marine applications. Biomimetic approaches based on deep-sea organisms have led to advances in materials science, robotics, and engineering design. The solutions that evolution has developed for surviving in extreme deep-sea conditions often suggest novel approaches to human technological challenges. The study of deep-sea extremophiles, organisms that thrive in extreme conditions, has applications for biotechnology, medicine, and astrobiology. Enzymes from deep-sea organisms can function under conditions that would destroy conventional biological molecules, making them valuable for industrial processes and research applications. Deep-sea research contributes to our understanding of the fundamental limits of life and the conditions under which biological processes can operate. This knowledge informs our search for life elsewhere in the universe and our understanding of the potential for life to adapt to changing environmental conditions on Earth. The deep sea serves as a natural laboratory for studying processes that operate over geological timescales, from the formation and evolution of ocean basins to the long-term cycling of elements through Earth systems. These studies provide context for understanding current environmental changes and predicting future conditions. Looking toward the future, deep-sea exploration will likely become more affordable and accessible as technologies continue to advance and costs decrease. This democratization of deep-sea exploration could accelerate the pace of discovery and expand participation in deep-sea research to institutions and nations that currently lack the resources for major exploration programs. The next generation of deep-sea explorers will have access to capabilities that current researchers can barely imagine. Artificial intelligence, advanced robotics, new materials, and novel energy systems will enable exploration of previously inaccessible environments and detailed study of phenomena that we can currently only glimpse. The integration of deep-sea research with other Earth system sciences will provide increasingly comprehensive understanding of how our planet functions as an integrated system. This understanding is essential for addressing global challenges such as climate change, biodiversity loss, and sustainable resource management. As our knowledge of deep-sea environments grows, so does our appreciation for their complexity, beauty, and importance to planetary systems. The deep sea represents not just a frontier for scientific discovery, but a reminder of how much we still have to learn about our own planet. The mysteries that drew us into tonight's exploration, the creatures that seem impossible yet thrive in crushing darkness, the chemical gardens blooming around volcanic vents, the vast plains where time moves slowly and change unfolds across millennia, all of these wonders remind us that Earth still holds secrets waiting to be discovered. Every descent into the abyss reveals new questions, new connections, new possibilities for understanding life and our place within it. The deep sea teaches us humility in the face of vast unknowns and patience with the slow pace of discovery in extreme environments. It reminds us that exploration and wonder are essential parts of human nature, driving us to seek understanding even in the most challenging and remote places. The bioluminescent displays that paint the darkness with living light, the ancient seafloor that records Earth's history in layers of sediment, the creatures whose very existence expands our definition of what life can become. All of these phenomena invite us to reconsider our assumptions about the world we inhabit. As we continue our journey of discovery in Earth's final frontier, we carry with us the knowledge that every question answered reveals new mysteries to explore. Every species catalogue suggests countless others awaiting discovery. Every ecosystem studied demonstrates connections we never suspected existed. The deep sea waits patiently for our return, its secrets preserved in the cold, dark waters that have remained unchanged for millions of years. In these hidden realms, time moves differently, and the urgent pace of surface life gives way to rhythms measured in geological epochs rather than human generations. Tonight's exploration has taken us through underwater mountains taller than Everest, across plains wider than continents, and into communities of organisms that redefine our understanding of survival and adaptation. We've encountered creatures that create their own light in absolute darkness, animals that thrive in conditions that would instantly destroy most surface life, and ecosystems that operate on principles unlike anything found in familiar terrestrial environments. The deep sea's influence on global systems extends far beyond its hidden boundaries. The circulation of deep waters affects climate patterns around the world. The carbon stored in deep sediments influences atmospheric chemistry, and the organisms living in the abyss contribute to biogeochemical cycles that maintain conditions suitable for all life on Earth. Our planet's ocean represents the largest continuous habitat on Earth, yet it remains largely unknown to us. Each expedition into these depths brings back evidence of complexity and beauty that rivals any environment we've explored. The deep sea challenges us to expand our imagination, to consider possibilities we never thought to envision, and to recognize that our small planet still harbors realms as alien as any we might discover among distant stars. The creatures of the deep sea have evolved solutions to challenges that push the boundaries of biological possibility. Their adaptations to extreme pressure, eternal darkness, limited food resources, and chemical environments that would be toxic to surface organisms demonstrate the incredible flexibility and creativity of evolutionary processes. These adaptations often involve partnerships between different species, cooperative relationships, that allow organisms to survive in conditions that would be impossible for any individual species to endure alone. The symbiotic relationships between deep-sea animals and chemosynthetic bacteria represent some of the most intimate biological partnerships on Earth, with organisms so integrated that they function as single units. The discovery of chemosynthetic ecosystems around hydrothermal vents fundamentally changed our understanding of the requirements for life. These communities demonstrate that life can exist independently of sunlight, deriving energy from chemical reactions rather than photosynthesis. This discovery has profound implications for our understanding of life's origins and its potential existence in other environments throughout the universe. The geological processes that shape the deep sea floor operate on scales that dwarf human experience. Mid-ocean ridges create new seafloor through volcanic activity that has continued for billions of years. Deep-sea trenches mark locations where entire oceanic plates slide beneath continents, recycling seafloor back into Earth's interior. These processes occur slowly by human standards, but have shaped our planet's surface over geological time. The deep sea preserves records of Earth's history that extend back hundreds of millions of years. Ice ages, periods of global warming, mass extinction events, and the gradual evolution of atmospheric composition are all recorded in the layers of sediment that accumulate on the deep sea floor. These records provide crucial information about how Earth systems have responded to environmental changes in the past. and what we might expect as conditions continue to change. The mineral resources of the deep sea represent some of the largest untapped reserves of materials essential for modern technology. Manganese nodules scattered across abyssal plains contain metals needed for batteries and electronics. Hydrothermal vents host deposits of copper, gold, and rare earth elements that could supply human needs for centuries. However, accessing these resources without destroying unique ecosystems presents enormous technical and ethical challenges. The deep sea serves as a refuge for species that have disappeared from other environments. Living fossils, organisms whose body plans have remained unchanged for millions of years, find sanctuary in the stable conditions of the deep ocean. These living links to Earth's past provide insights into evolutionary history and the factors that promote long-term survival. Climate change is beginning to affect even the deep sea, altering temperature patterns, circulation systems, and chemical composition in ways that could have far-reaching consequences. The deep sea's role in global climate regulation makes understanding these changes crucial for predicting future climate conditions and developing effective responses to climate change. Ocean acidification, caused by the absorption of excess carbon dioxide from the atmosphere, affects the ability of many deep-sea organisms to build shells and skeletons. The cold temperatures and high pressure of deep waters make them particularly susceptible to chemical changes, potentially affecting entire ecosystems in ways we are only beginning to understand. The vast scales of the deep sea mean that human impacts, while locally significant, affect only small portions of the total deep ocean environment. However, the connectivity of ocean systems means that changes in one region can influence conditions thousands of miles away. Understanding these connections is essential for predicting the cumulative effects of human activities on deep-sea ecosystems. Conservation efforts in the deep sea face unique challenges due to the remote locations involved, the high costs of monitoring and enforcement, and the limited knowledge available about most deep-sea ecosystems. International cooperation is essential for effective conservation, since most deep-sea environments lie beyond national jurisdictions. The development of new technologies for deep-sea exploration continues to reveal capabilities that seemed impossible just a few years ago. Autonomous underwater vehicles can now operate for months at a time, collecting data from remote locations that would be prohibitively expensive to visit with traditional research vessels. Advanced imaging systems can document deep-sea organisms and behaviors with unprecedented detail. Artificial intelligence and machine learning are beginning to revolutionize deep-sea research by enabling automated analysis of the vast amounts of data collected by modern exploration systems. These tools can identify new species in video recordings, detect patterns in environmental data that would be impossible for humans to recognize, and optimize exploration strategies based on prior discoveries. The integration of satellite technology with deep-sea research is providing new perspectives on ocean processes and their connections to global systems. Space-based observations can detect surface signatures of deep-water upwelling events, track the movement of ocean currents, and monitor changes in ocean chemistry that reflect deep-sea processes. The democratization of deep-sea exploration through reduced costs and improved accessibility is beginning to involve new participants in discovery efforts. Citizen science projects allow volunteers to contribute to research by analyzing images and data collected from deep-sea expeditions. Educational institutions are developing programs that give students opportunities to participate in real deep-sea research projects. The economic potential of deep-sea resources continues to attract commercial interest, but sustainable exploitation will require careful management based on scientific understanding of deep-sea ecosystems. The challenge lies in balancing economic development with environmental protection in environments that we are still learning to understand. The deep sea offers opportunities for testing technologies and strategies that could be useful for space exploration. The isolation, extreme conditions, and communication challenges of deep-sea environments provide analogues for the conditions that human explorers might encounter on other planets or moons. The philosophical and cultural significance of deep-sea exploration extends beyond scientific discovery to influence how we think about humanity's place in the natural world. The deep sea reminds us of the limitations of human knowledge and the importance of maintaining humility and respect for the natural systems that support all life on Earth. As we conclude tonight's journey into the depths, we carry with us images of a world that exists parallel to our own yet remains largely hidden from our daily experience. The deep sea represents both the known and the unknowable, the familiar patterns of life stretched to their limits and beyond, into realms of possibility we are still discovering. The bioluminescent creatures that create galaxies of living light in eternal darkness, the massive organisms that move slowly through the abyss like living mountains, the delicate relationships that connect organisms across vast distances and extreme conditions, all of these phenomena remind us that our planet continues to harbor mysteries as profound as any we might discover in the far reaches of space. The deep sea waits for us, patient and eternal, holding its secrets in the cold embrace of crushing depths. Each return to these hidden realms brings new understanding and new questions, continuing cycles of discovery that have only just begun. The abyss that once seemed empty and lifeless now reveals itself as one of the most diverse and dynamic environments on our planet. Tonight's exploration has taken us to places where human beings have never set foot, where the very concept of footsteps becomes meaningless in the weightless realm of dense, dark water. We've encountered organisms whose existence challenges our most basic assumptions about life, environments that operate according to principles we're still learning to understand, and processes that connect the deepest depths with the most familiar aspects of our surface world. The journey continues, carrying us deeper into mystery and closer to understanding, revealing connections between the most remote corners of our planet and the everyday experiences that define human life. In the deep sea, we find not just new species and new environments, but new ways of thinking about life itself, new appreciation for the complexity and resilience of the natural systems that sustain us all. The darkness that initially seemed so forbidding now reveals itself as a canvas for some of nature's most spectacular displays. The pressure that would crush human bodies in an instant provides the foundation for ecosystems of incredible beauty and complexity. The isolation that separates deep-sea environments from surface influences creates laboratories where evolution experiments with possibilities that surface life never explores. As we drift toward rest, carried by currents, as slow and patient as those that move through the deepest trenches, we take with us the knowledge that our planet still holds wonders we have barely begun to imagine. The deep sea continues its ancient rhythms, indifferent to human schedules, yet intimately connected to the systems that make human life possible. In the deepest parts of the ocean, time moves differently. Days and nights have no meaning in the eternal darkness. Seasons pass without notice in the stable temperatures of the abyss. Years and decades represent brief moments in the long cycles that govern deep-sea processes. This different relationship with time offers perspective on the urgent pace of surface life and the longer rhythms that connect us to geological and evolutionary processes. The creatures we've encountered tonight continue their ancient dances in the darkness, following patterns established over millions of years of evolution. Anglerfish wave their lures in the darkness, attracting prey with lights that have glowed unchanged since long before humans walked the earth. Giant tube worms cluster around hydrothermal vents that have supported similar communities for thousands of generations. Deep sea currents continue their slow circulation around the planet, carrying nutrients and heat on journeys that span decades and cross entire ocean basins. These currents connect Arctic waters with tropical seas, surface productivity with deep-sea ecosystems, and local weather patterns with global climate systems. The sediments of the deep sea floor continue their slow accumulation, adding new layers to records that stretch back millions of years. Each microscopic particle that settles to the bottom carries information about surface conditions, biological productivity, and chemical processes that future researchers will use to understand how our planet's systems have changed over time. In research vessels scattered across the world's oceans, scientists continue their patient work of discovery, analyzing samples collected from depths that challenge human technology and reveal new aspects of life on Earth with each expedition. Their work adds incrementally to our understanding of deep-sea systems, building foundations for future discoveries and conservation efforts. The mysteries remain vast, extending far beyond the reaches of our current knowledge and technology. Each answer raises new questions, each discovery suggests new realms of possibility. Each expedition reveals how much more there is to learn about the largest habitat on our planet. The deep sea holds its secrets lightly, revealing them slowly to those patient enough to undertake the challenging work of exploration and discovery. In its darkness, we find new forms of light. In its isolation, we discover unexpected connections. In its extremes, we uncover new possibilities for life, a new understanding of the world we share. Tonight, as you rest, the deep sea continues its ancient processes, indifferent to human time, but intimately connected to human survival through the countless ways that ocean systems influence climate, weather, and the chemical composition of our atmosphere. The abyss that seems so remote actually reaches into every aspect of life on Earth through connections we are still learning to trace and understand. The exploration continues, carried forward by human curiosity and the drive to understand our place in the natural world. Each generation of explorers builds on the discoveries of those who came before, adding new knowledge and new questions to the growing understanding of Earth's final frontier. The deep sea waits, patient as only geological time can be patient, holding its wonders and secrets until humanity develops the tools and wisdom needed to approach them responsibly. In that waiting, there is both challenge and promise, both mystery and the assurance that discovery and wonder will continue as long as there are humans willing to ask questions and seek answers in the vast dark depths of our planetary ocean. In the deepest places on Earth, to where no human eye has ever looked directly upon the sea floor, where pressure and darkness create conditions unlike anywhere else in our solar system, life continues its remarkable experiments with possibility. There, in the abyss that once symbolized the limits of the unknown, we find not endings but beginnings, not emptiness but abundance, not silence but the subtle communications of organisms adapted to conditions that stretch our understanding of what life can become.